All right, welcome back, everyone. Today is lecture 20. And before I begin, okay, people who are online, can you hear me? Okay, thank you, Trevor. Okay, so until now, like until lecture 19, we have actually covered the important topics in machine learning and AI and the ones that are widely used. We have also covered like 3 different paradigms, supervised learning, unsupervised learning, reinforcement learning. So now the topics that begin from today onwards, these are advanced topics. And the way I've decided to go about these is that we'll focus more on the intuition side, and maybe I'll provide some implementation for you because we don't have any homeworks on these topics. So that like in future, if you ever need to go and work with this, and because you haven't worked on a project yourself, you can just like go and refer to that like that to get started. So if you just like scroll down in the lecture notes, you'll find a link to my Colab notebook for these topics. And just for the reason that you didn't get to implement these, but they're there so that you can get started. And like with some basic data set, obviously I'm trying to do less work as compared to what like you've been doing. So, but you still have some starting point for these topics. Okay, so as I said, this is an advanced topic, and this is known as Bozeman Machines. And today we are going to discuss like the intuition behind this and some math behind it as well. But there is this paper, if you go down to the reading section that I've provided, this paper is actually more like a tutorial that talks about Bozeman machines in like a fair amount of detail. So you can go there and check that as well. But I feel like the key takeaway from today's lecture should be like what Boltzmann machines are, what type of problems they should be applied to, and how these work. Like what's the basic intuition, what's the architecture, and how does the training happen, right? And so, of course, as I said, you have a link to the Colab notebook. You can always refer to that. Fine. So until now, as I said, we have looked at neural networks in quite an amount of like a great amount of like detail. And you've looked at feed-forward networks. You have looked at convolution neural networks. You've looked at recurrent neural networks. And if you think about them, like in general, there is some a kind of information or some like data flowing in certain directions. So if you remember like the feed-forward network, let me quickly remind you. So you have essentially like an input unit, right? And a hidden unit, and let's say like some output. And there is like some input coming in and then some input going in here. And then eventually you have like some output coming out, right? And then if you remember in our convolution neural network, you had like some layers, some convolutions added to like, let's say my images. And then maybe I apply some more, like maybe striding, or it depends like whatever we're doing. And then eventually like fully connected layers, and then you're getting some output. In recurrent neural networks, you had like this unit in which you were sharing information. So there was like this flow of information or data. And then there was something that was like leading to like a recurrent flow of information as well. So one thing that's like common in all these neural networks is that there is this direction in your computational graph. When you think about these, there is like this arrow that points to some direction in which your information is flowing. And then obviously like you have the backward pass in which we are like back propagating and computing the gradients, right? So the fundamental difference between these type of models and the model that we're going to look at today, that's the Bozeman machines, is that it's not like the way we represent it, it's like an unidirectional or like a graph that's fully connected but does not have any direction. So the units or like the layers or the neurons, so to say, in like in this neural network, is such that we don't have any direction in which the information is going to flow. So that means it can be in both directions, right? So that's the fundamental difference. And so let me quickly show you this. So this is like a high level sort of representation of a Bozeman machine that you have nodes, of course, and then you have like, so we are distinguishing between visible nodes and hidden nodes. And obviously we're going to like go into the details of like how they are different from one another. But from the perspective of this network, there is no differentiation between visible nodes and hidden nodes. It's just that these are a bunch of nodes that are all connected always, right? So as you can see, they're all connected. There is no direction in which information is flowing. That means information can flow both sides, right? So like a quick sort of idea that defines Boltzmann networks or like Bozeman machines, so to say, is that the nodes are connected always. So it's like this is an undirected graph, right? So that's the first sort of way of thinking about the architecture of this. Okay, so if this is an undirected graph, and you can see that this is like there are some visible nodes, there are some hidden nodes, but you don't see any output coming out of this. So maybe like you're thinking that there is some information in there that I'm like maybe feeding in through the visible nodes or the input layer. And then there are some hidden nodes, maybe I'm doing some computation there, right? That's what nodes mean. And then what is the output that's going out of this? Well, actually, there is no output that goes out of this. It's high level, like a representation of some data. So basically, it will try to learn some input distribution, so to say. So we are going to provide it with some data. It's going to learn the representation of that data. And then once it has learned that representation in terms of like these, so there will be some weights that are assigned to these edges. And those weights in some way will be a way to represent how my data is, what my input like training data is. Okay, so if you think about these nodes are nothing but some kind of states. Let's say like we are looking at some problem, and a very good way of like understanding Bozeman machines is like a nuclear setup, right? A nuclear reactor or something. And then it has like a lot of parameters, right? What temperature are we maintaining? What pressure are we maintaining at like different places in the nuclear reactor and so on, right? And like if we think about these different values or these different parameters, those values would be like the values in these nodes. And so all of these nodes taken together would represent a nuclear reactor in like the best form possible, right? In its working form. So like, why is this like this kind of representation useful? It's useful because if you think about like a nuclear power plant, for example, right? And if we are like trying to predict when is it going to fail or some failure is going to happen, and if we are using like supervised learning approach, then we need labeled data. So then we should have those examples when it failed, which is pretty rare, right? I mean, some like huge like failure has to happen so that we have those examples as well to train our like supervised algorithm, right? So for those type of problems where that kind of data is not available, I need to learn the system as a whole so that I have like these nodes that represent the usual values that the system has, right? So obviously I'll feed in a lot of data from like maybe from everyday working of this nuclear power plant, right? And then I'll have a system that is there so that like each of these nodes represents some usual level of temperature, pressure, or whatever like parameters are there. And if something goes wrong, right? So like one of these nodes will have a different representation from the existing system. And the moment that happens, I just know that there's something that's not working. Right. So again, like I'm repeating this, but the like high level intuition of this Boltzmann machine is that this is a representation of some input data, and it tries to learn that system, so to say, and it tries to maintain that system. And if I just like go away or deviate from that system, I just know that there is some issue going on, right? And so this is like an unsupervised learning approach because I don't have any examples to look at. I just like train my network so that so that I learn some system, and then I'm able to use that for prediction. And of course, we're going to see like look at examples and other things. So like another way of thinking about this is that these nodes are generative in the sense that it like my network is going to generate the values. The network itself is going to generate values. And the other thing is like we have this labeling of hidden nodes and visible nodes for our own understanding. But actually, when the network will start to train, it does not distinguish between hidden and visible nodes. For it, like all the nodes are similar, and it's going to keep assigning these weights to update the values and generate some values there, and eventually reach some equilibrium. And we're going to define what that equilibrium is. Like when does it like stop training, and when does it like stop changing the weights and so on, and how the weights change. But that's the fundamental idea behind Bozeman machines. And then moving on. Yeah, so as I said, this is a representation of a system. And this is an unsupervised learning approach. And overall, this is known as a stochastic deep learning model. And we'll see why. So whenever like you're thinking of any stochastic deep learning model, Bozeman machine is one of them. All right. So before we jump into like how these nodes are updated, what values do those edges have and how those like edges are updated, before that, I wanted to go into something that's known as energy-based models. And the idea of, so like the thing behind the way we train Boltzmann machines is by borrowing this idea from thermodynamics. And in thermodynamics, there is something that's known as energy-based models. And we are going to utilize them to train our Boltzmann machines. Okay, so let's quickly look at what these are. And to give you a high-level idea of what this says, like what energy-based models say is that, like, let's say I'm in this room, and the way this like the air is dispersed in this room, or the air molecules are dispersed, is that they are like equally distributed in some ways, if you think about it, right? So let me just like draw this so that it becomes. And you must have seen this example maybe in school sometimes. I remember like in some science classes, they used to have this example. And so like we have actually borrowed that idea from there and used to train Bozeman machines. So let's say this is like some room, and you have like these air molecules that are usually, and we know it from like our knowledge of like air as such, that it will spread out as much as it can within that room if it's a closed room, right? However, like there is nobody like who's stopping us from having this kind of a configuration of these molecules, right? That's also a possibility that like these molecules could just like cluster together in some corner of this room. But like in all such physical systems, high level, what's happening is that these systems try to minimize the overall energy, because as these molecules, they come closer to one another, the energy that's associated with that system rises. So the probability of having a system with higher energy is usually low in physical systems, and it's extremely low. And because of that, and this can be actually described by something that's known as Bozeman distribution. Okay, so let me write it down. And that's where the name comes from. Okay, so what does it like tell us? Like mathematically speaking, we are saying that the probability of being in some state I in a physical system, right, is equal to, and this is maybe familiar, I'm not sure if this is familiar or not, this epsilon I is in some ways representing the energy of the system in state I, right? And that divided by KT, K is some constant, T is temperature. Obviously, this equation was borrowed from thermodynamics, and that's why the temperature and the energy. But we'll see how it fits into our Bozeman machines, right? That's important for us. And this divided by the sum of like all possible states for this particular system, and then epsilon j, right? So the K is like some constant, T is temperature. Now, if we just like look at this equation and see the relationship between the probability of the state being in I and this energy state of my like state I, right? I can tell that the probability of like having a high energy system is small, is low. So the probability is like for having a lower energy system is usually higher, right? You can see the relationship between this and this energy equation. This is what it's telling us. And this has been observed in so many physical systems. All right. So basically, like this is the lowest energy state possible for my air molecules, and that's why they spread out. That's why they diffuse, like and try to I would say uniformly distribute in a given like closed room. Okay, so my Bozeman machines are constructed on this principle. Okay, so what I'm trying to do is I will have some way of representing my weights in such a way that they represent this energy part in my probability equation, right? So I'll have my weights adjusted in some ways so that they represent the lowest energy possible in my system, in my Boltzmann machines. So that's the idea that we are trying to. So basically, my system will try to find the lowest energy state possible. And hence, I'll keep updating my weights until I get that. Right? So basically, what I'm saying is my weights will dictate, like, what are weights? Weights are the values on my edges. So my weights will in some ways dictate the energy of the system. So basically, using this energy equation, I'll say that this is the weight of my system, and I'm going to come to that probability which is like lowest in terms of the weight values. So in some ways, so there is like more, I would say, mathematics behind it. In some ways, like we have this energy related to the weights. And so the way we train the network is that we come down to those weights that lead to the lowest energy possible, or the state where like you don't have a high energy. So does that like make sense, or there are some doubts? High level, it makes sense, right? We are trying to come up with a system which is like a low energy system, and then energy is nothing but the weights that are there on the edges. That's the intuition behind Bozeman machines. Yeah. All right. So that's why we talk about energy-based systems. As I said, all physical systems try to maintain lowest energy state. And these Bozeman machines are developed with a similar intuition. That means I learn the weights such that I can dictate the lowest energy of my system. And then I'll describe my energy as like some function of my weights. Okay. So having said that, if we go back and check this network, this Bozeman machines, so this is like the most basic like architecture of Bozeman machines. However, we don't really use them in practice. What we do is we use something that's known as restricted Bozeman machines. The very first reason is like, I don't know if you noticed or not, like my visible nodes are like usually in any neural network, we had like the flow of information, but the input nodes were not connected to one another. Or like even in a hidden layer, the nodes were not connected to one another. They're definitely connected like from one layer to another, but not like amongst themselves. And that's what's happening here. So that means like as we increase the number of nodes, my connections are going to like be huge, right? And so training this network becomes like really difficult. That's the first thing. So this is like hard to implement. And this is hard to implement because obviously the number of connections, like every node is connected to every other node. And so as I start to increase those, depending on the size of my data or depending on like whatever problem you're trying to solve, this is going to be hard to train. And so what I'm trying to like, what I can do is I can make some restrictions to this network. And so the first restriction that I make is that maybe I can get rid of these connections within the like in between these visible nodes. Or maybe I can get rid of like the connections between like the hidden nodes. Rest of it stays the same. So let every node from my input be connected to everyone in my hidden nodes, but let's not connect them with each other. And then let's see what happens. So this was like, I think this idea came about in like the 1980s or early 90s. And this is known as the restricted Bozeman machines. And I think I have a paper that talks about this. And this was obviously invented by Geoffrey Hinton. And this is an algorithm that's used for dimensionality reduction, classification, mostly collaborative filtering. So this is like in recommender systems and also in feature learning topic modeling. So we'll look at it from the perspective of recommender systems. That's like recommending movies or items to customers on online platforms, right? Okay, so what is like a restricted Bozeman machine? Well, it's, as you can see, this network, and just like don't focus on like what the nodes are saying for now, because I'm going to talk about that shortly. But just let's focus only on the architecture of this. So these are my visible nodes, the blue ones, and these are my hidden nodes, the red ones. And as you can see, every node is connected to every node in like the other layer. But these nodes are not connected to one another, right? So that's the fundamental difference. The rest of it stays the same. All right. So now we've talked about the architecture of Bozeman machines and also restricted Bozeman machines. And now we know the overall intuition of what's going on. We are going to train this network so that there is like, this is a minimum lowest energy state possible. And basically, I'm trying to learn some underlying distribution from my data. Okay. All right, so here you can see like some inputs that's like movies, and then there are some nodes that are representing some genres or actors, awards, director, whatever. But like from the perspective of the network itself, there is nothing like this. There is just like some data that's like input, and then there is like some features that that network creates. Okay, so how does that happen? So first of all, let's think about like some input data from like a movie recommendation, right? So usually this is how it looks like. Let me quickly show you. And this is like, let's say user 1, user 2, I don't know, user 10. And then we have some movies here, right? So movie 1, movie 10, right? And let's say like this user rated this movie. So the user rated 1, 0, maybe 0. This user rated this 0, 1, 1, 0, 1, 1, and so on, right? So like we have like these ratings. Let's consider like a very simple model where you have just like ratings of zeros or ones you like or you dislike, right? And there would be some like user here who would have watched like this movie, but like they don't have a rating for this one and this one. So the recommender system problem is that I need to predict the rating for user N for movie 2 and movie 10 based on the data that I have for other users. So that's the problem that we are trying to solve. Okay. Now, the way Bozeman machines or restricted Bozeman machines work is that it's going to look into this data, right? And it's going to extract this information and come up with some representation of my input. Well, what does that mean? For example, let me give you a quick like idea. Let's say I had like some movie 1, movie 11, and movie 13, right? And every time like some user likes this movie, they always dislike these. And if they dislike this movie, right, they always like these two movies, right? So in some ways, like there is some kind of a relationship amongst these movies, right? So in some ways, this relationship can be captured in this node here. So the way the network is looking at it is that this is this genre A, some genre like action or I don't know, some drama or whatever. That's like for our understanding. But internally, the network has figured this relationship between these movies and it has come up with a value for that. Similarly, let's say there are users who whenever they like this one, they always like this one. Maybe that's also happening, right? And if they dislike this one, they always dislike the other two. So there is again some kind of relationship, and maybe the actors are the same in all the movies. When they like the movie, the actor is the same. When they dislike, that actor is not there in the movie. So my network is going to learn that relationship, not exactly based on like that actor's name or something, but the implicit relationship that exists. Right, so it is pretty complex. As I said, like these are advanced topics, so it's not that straightforward. I'm not giving I'm not giving the input as this is the actor and this is the genre and this is the like the award one and so on. Right, but based on the data, it's going to keep and we are going to keep feeding this data until it learns and then until it converges. Right, and we'll see like what are the conditions for convergence and so on. All right. So that's like the architecture. So what I'm going to do is I'll keep feeding this network with this data, right? Until it has learned and has like some values that are allocated to these. And then what I'm going to do is a new user is going to come, right? And then let's say the new user has some rating and some of them are missing. Okay, so let's say the new user has like 1 for this movie and maybe 1 for this one, and then 0, and then 1, and these two are like missing. So my goal is to go and predict the ones that are missing. Right, that's what I'm going to do. So I need to predict this one, and I need to predict this one. Right? Okay. So what my network has already learned from these movies are these weights on these connections. Right? So these weights have been learned by from my data. So one way of thinking about this is that I'll have like some kind of connections, and like obviously this node is connected with all of these, right? But there are weights that are assigned to these, right? So depending on the weights that these like edges have, I will have some way of thinking about like okay, this actor this user likes this movie. And let's say this movie was like an action movie, right? And also this actor likes this movie. This was also an action movie. So this particular node somehow learned that this like user likes action movies, and so that's a positive, right? And let's say this user disliked this one, and this was a drama based movie. So what will happen is my network would learn that like this should be a negative for this user, right? Because my network already has this like way of figuring out, because I already fed in all that data and it has come up with these features, right? So basically I can come up with like plus or minus, and yes, so the like maybe this user likes this actor, maybe this user always watches like this award winning movie and dislikes this director, right? So once like we have this like positive and negative figured for this like new user, now comes the important part. That is like I will have to go and reconstruct my inputs in such a way that I can predict these unknown values. Okay, so how like, and again, like this is all high level based on like the weights that my network would have learned from my data. Let me like repeat or put things together. So I'm doing this for some user M that was not there in my data, but my network was already trained on that data. So my network represents this data set in some way. Okay, so like it's different from the idea of like training a network and then looking for a new data set. And of course, like we are trying to look for a new user, but my network is a representation of this data set. And based on this representation, my network has come up with some features. And those features like get a positive or a negative value depending on my test user that comes in, and like whether they like a particular movie or not. They will have some values. And based on the some values, I can give like some higher weights to like, for example, genre A and lower weights to genre B and so on. Right? So then what happens is that like I have to go backwards to see like where like this movie lies, because obviously this movie has not been rated by my user. But let's say that this movie had a very high weight for genre A, and then it also had a very high weight for this actor, and it had a high weight for like this director. So now because I have more plus than minus, right? So I can like maybe recommend this user like depending on whatever like higher weights I have, right? So basically I'll have to do a backward pass and see like where exactly does this movie lie, whether this actor likes this or not, how many positives are there for this, sorry, whether this user likes this or not. And so I have more positives than negative, maybe I will recommend this user this movie, right? Because I don't know how this user has rated. So basically, in some ways, I'm predicting the rating. So maybe I'll say, yeah, most likely the user will like. That's my predicted value. And in this one, again, I'll see, obviously, this node is connected to all these, right? So I will see which ones have the higher weights, right? So maybe this one doesn't have, is not like linked to this director, but it is linked to this award and to this genre. And so, and this actor. So more positives. Maybe I'm going to recommend that user this value, this movie, and so on. Right? I know this is, and as I said in the beginning of the lecture, this is like an advanced topic. But one thing to remember is that my network has learned a given system. Maybe this is like a ratings from some like Netflix or some like website. And then if a new user comes in, based on what my network has learned, I can do a forward pass and a backward pass and then recommend things to new users. Okay, so all of this looks good, but then how exactly are we reconstructing these, right? So I just like gave you a high level overview of, okay, internally my network learned these genres and like these actors, these awards, but basically for the network, these are just some features. These are just some features that have incorporated some form of, I would say, similarity from the movies and come up with these values, right? However, we are left with the most important question of like how these weights were like decided. And when I said I trained the network and my network reached that point of like lowest energy state, what does that mean, right? We don't know that. We just know that this is how um, my network is going to work, and this is how I'm going to predict an unknown value, right? So going back to, I think I have a paper. So here, this actually talks about this thing in detail. So this like talks about the architecture, about the learning. So if you have time, you can go and look at this article, and yeah, talks about this. Yes, I will discuss this. So let's like go back. Okay. So now, like we understand the architecture and we understand the overall intuition behind restricted Bozeman machines and how we are predicting things, but we don't know how to get the weights on these edges, right? And in order to do that, we use something, and it's a very well-known algorithm, and this is known as contrastive divergence. So that's the algorithm that we use in order to train our model and get the weights on those edges. Because based on the weights on those edges, we like it gets a positive and a negative value, and then eventually we can predict things like coming backward in the backward pass, right? So what exactly is this contrastive divergence? It's like an alternating technique to approximate like the values in my network. And let me give you a high level idea of like what goes on in this contrastive divergence. Okay, if you're looking at this picture, so what we are doing in every single pass in my network, as I'm like giving it more and more data, right? I have this input layer or my visible nodes, right? So the blue ones are the visible nodes and the green ones are the hidden nodes, right? So in the movie example, I saw that I'm using that data, and in some ways I'm creating these features or these nodes based on that data, right? That's how I created those features. And obviously I had them for my own reference that this maybe this feature means this, or maybe this feature means that, but that's for our understanding. Actually, for the network, it doesn't like mean a genre or an actor or an award. It just learned from the data, and it has like some representation of like a movie in some ways. So similar to that, I will have like these nodes created. So what I'm doing is I'm actually, and this X actually represents the input and H represents the hidden value. And you will initialize your network, or sorry, the edges with some random weights. And what happens in this contrastive divergence is that you don't update those weights. You keep the weights the same. All you're doing is like, this is my first pass. Like this arrow is my first pass. And I'm creating, or I am like generating this hidden layer using this input, right? And then remember when I talked about the movie example, I said we have to predict the ratings of those movies that were missing the ratings. And so in some ways I construct, if you think about it, I constructed that node based on the inputs of like the positives and the negatives that I got. So what I did was I constructed the hidden layer using my input, and then I reconstructed. So here, this arrow points to reconstructing the nodes again. That was the whole point of having this entire network connected to one another. So in every pass, and let me just like go back to the example. Like in the movie example, what I did was like notice these arrows here, right? These arrows in some way were passing the information, like let's say this movie was an action movie, whether it has a particular actor or not. And based on that, these values were getting activated in some ways. So some values were getting activated more than others because this movie like inherently had certain properties that weren't like making these certain nodes getting activated. So maybe it wasn't a part of a drama, so that was a negative. That means lower activation, higher activation, lower activation, right? So this was my forward pass. And so what I was doing was basically based on my information, based on my data, I'm creating these nodes or I'm creating these features. And then what happened was I wanted to do something about this node because this did not have a rating. So I did a backward sort of reconstruction from all these nodes. And the ones that were higher, had higher activations, right, were the ones that are going to activate this, right? And so based on the properties of this movie from like what my network already learned, right, I will know that yes, this movie belongs to this genre, right? And then yes, this movie has this actor, and yes, this movie has this award. So maybe I should recommend it, right? So I reconstructed this node by actually getting like the inputs from all the hidden nodes, right? So that's exactly what happens in this contrastive divergence. What I'm doing is I'm continuously getting my input, and then I'm creating my hidden nodes, and then using my hidden nodes, I'm reconstructing my input. And then using my input, I'm reconstructing my hidden layer again. And this goes on and on and on. And so the question arises like, until what point does it go on? Because initially I said that I'm going to randomly initialize my weights, and then I'm not going to change the weights. I'm going to keep them that. And then keep like using those, I would want to reconstruct my nodes. So you must be thinking that if I constructed my hidden layer and then again reconstructed the input, most likely I got the same input. Yes or no? Should I get the, like, if I started from x0, right, and then move on to x1, and I kept the weights the same on each of the edges, are there any like chances that I would go and get a different input, like different values of the nodes, or am I going to get the same values? Anything, like this is not a test. I mean, the first time I read about Bozeman machines, I just thought that it's never going to change. But actually it does, because if you think about it, like let's focus on this movie 2, right? So movie 2 is like created by getting all these inputs from all the nodes, all the hidden nodes. But then that's not the only node that is being reconstructed by these. So in some ways, what's happening is there is some kind of if we just like focus on one node, it's like it is highly likely that it can get a different value, because then like they have to distribute the value amongst the other nodes as well. That's the idea, and so they do change, right? Otherwise, there was no point of like having restricted Bozeman machines. So obviously, like that could be a guess, right? That they do change. Otherwise, why are we doing this pass? But then the point is that we are doing so many passes because eventually you do come to that point wherein the distribution of those weights tends to get like smaller and smaller. And there would be a point like let's like we are representing it using infinity. When you like input this x infinity, you get the same hidden layer that was like before, and then you get like the same input nodes again. So there comes a point like that. And then what you can do is you just stop. So you have like in some ways reached that equilibrium point, that lowest energy state in your system, because by moving anything else, by changing any other weights or anything, will not like change the overall like configuration of my system. Right. And again, I'm like talking about the intuition. There is like more in-depth math behind it. And I would refer everybody, because this is like anyways a difficult topic. You should go to this one. And as I said, this is, although this is a paper, but actually this looks more like a tutorial that talks in detail about like how this happens. So okay. Energy-based, I think they do talk about contrastive divergence. Okay, we're going to come to this part soon, but let me quickly go back to see. Okay, anyways, as I said, it's like more, it's less of a paper and more like a book or like almost a chapter on this topic, Bozeman machines. But coming back to contrastive divergence, yes, I think I talked about the reconstruction part. Okay, this method of like continuously updating, like continuously doing this reconstruction is sometimes known as Gibbs sampling, if you've heard that word before. And what was like, we keep reconstructing my inputs until that like convergence point is reached, wherein like we stop like getting a different outcome. Okay. So why is this like helpful and what exactly are we doing here? So again, to give you an intuition of what's going on is that we have this equation, and I'm going to write it down. And again, I've taken it from the paper itself. So let me just write it down here. Okay. Initially, I said that those weights are in some ways, or like if you remember the Bozeman distribution equation, what we do is the energy part in some ways is related to my weights, right? So basically, my weights decide the energy of my system. Right. So whenever I'm talking about energy, it's essentially the weights, but there is a more like intricate relationship. There is an equation that describes the relationship between energy and weights, but I'm regardless using them both as like interchangeably to simplify things. Okay. But just remember whenever I'm talking about the energy of the system, I'm talking about the weights because the weights are driving the energy of the system. Okay. So if we look at like how this entire process goes on in contrastive divergence, is something like this. So let's say that you have some way of representing the overall energy of the system. And this is my data space. And this is how the paper describes it. So I just like took it from there. So what we're trying to do is, if we can describe the existing energy of the system at something like this, right? And of course, my weights are going to weights are going to define the shape of the energy curve. And let's say that like I initialize my state somewhere here. So I initialize my weight somewhere here. I like through my contrastive divergence, I want to move somewhere in this like direction. So very similar to what we try to do in gradient descent. Like we try to minimize the loss here. We are trying to minimize this overall energy of the system, right? So we want to move in this direction. And so with every subsequent pass, right? Every time we pass, we do the like the input and the reconstruct the input again. That's called one pass, right? So with every subsequent pass, this is what we want, right? This is what we want. We wanted to minimize this. And there is like an equation that's provided in the paper. The way we can describe this process is that, like, let's say I can have the log probability of some state in my system, right? So I'm like, I know I'm like simplifying this a lot, but I think as long as you get the intuition, that's fine, right? So what this equation is telling us that for some state C, the log probability or the change in this log probability with respect to some weights, and obviously I'm not changing the weights, but I'm trying to see like what could be that change, right? So that can be described by something like this. And again, I took it from the paper. So the initial state and like minus the final state. Okay, so what we are doing throughout this process is we want to adjust the weights in some ways such that eventually, like after all those passes, we can come down to somewhere here. And that is going to be my lowest energy state. And then I would say that like my algorithm is converged and I've learned the entire system as such, right? So like how can we do that? Well, obviously we saw this here that in order to learn this entire system, I'll have to do like infinite passes, and this looks like some very inefficient way of doing this, right? Like how long should I go on? Like this is like infinite until I come to that state when I have like equilibrium and nothing is changing, and so that's the lowest energy state. So what they go on and talk about and actually prove that in the paper is that you don't have to do all those passes. You can actually learn this entire, and you can actually learn the lowest energy state just by doing the first pass, believe it or not. So basically, this is known as contrastive divergence 1. So whenever you come across that term, contrastive divergence 1, that means just like one pass. And one pass means just this part. Let me highlight it. Okay, so according to the paper, this pass, like this one, is sufficient to get to that lowest energy state because there is no like that curve would be defined by my weights. And eventually I'll reach to that point. There is no like pre-existing function in which like I have to go to that minimum point. So I can do some like update in my weights to get that that minimum point right then and there in some ways. right? So that's what this like theorem further talks about, and you can like go into the details of the math if you're interested. It says that it's enough, and this is known as contrastive divergence one, that one pass is sufficient to know what could be the possible like minimum energy, and you can like let the system learn using that. So there is a trick that they're showing, I think, in the paper as well, that like the moment you know the first two. Uh, this is not the exact thing, but yeah, like let's say this, like the one on the right is the energy curve that I talked about, which is a function of weights, right? And I know that my initial state is somewhere, and I know that the second, like after the first pass, my system is somewhere else. So I know the direction in which I'm moving right now. And based on that, I can somehow estimate where my lowest energy point could be. So I don't have to do all the passes. So that's the fundamental idea. So I could, like just by using the first two passes, I know that this is the direction I'm moving in. And so based on that direction, I can estimate this is going to be the lowest energy. So I don't have to like physically do that training part, right? Again, a lot of math goes before we actually come to that point, but I just wanted to give you an intuition and not make you overwhelmed with so much of information. But just like think about it like high level, what's going on is that I can change the shape of this curve according to some prediction that I can make based on like the direction in which I'm moving just after the first pass. Because I decided the curve like this, the shape of this energy curve. It's nothing but a function of my weights. So I can change that shape and get the minimum faster than I would usually, right? So that's the high level idea of like what's going on here. All right. So having said that, let's go back to the lecture notes. Why won't it let me go? All right. So like in this part and this one, we talked about what are restricted Bozeman machines and how they learn. So like key takeaways are you should know the architecture of a restricted Bozeman machine. And then you should also know this contrastive divergence algorithm. There are different variants of this contrastive divergence algorithm. For example, we saw the CD1. You can also come across CD3, CD5 that have different sort of goals depending on the problem that you're trying to solve. Okay. Now, there are two more topics that although I wanted to cover, but I decided not to because they are further like very like advanced and they are like built on this idea of Bozeman machines. So if you are familiar with restricted Bozeman machines, most likely you can understand those. And I have provided these like important sources and important papers that you can actually go and read. But high level, like if you look at this, the first one is deep belief networks. So these are even more powerful models in unsupervised learning. But there is a slight uh, difference from what we just talked about. So deep belief networks actually have multiple restricted Bozeman machines stacked on top of one another. That's the first thing, as you can see, right? So this is RBM1, RBM2, and so on. So obviously the RBM itself is very complex, and then you have many of them stacked together. That's the first thing. The other thing is, I don't know if you can see well enough, it has these arrows, which we do not have in my restricted Bozeman machines because you can have a pass like both sides. So it's like, so here we do add some level of direction. And then in the final two layers, we do that, right? So when you're moving, like for example, layer one and layer two does not have direction. So both sides we can move. But here you have some kind of direction. And again, so basically you skip some layers and then you provide directions. And in some layers, you don't provide direction. So that's what like a deep belief network is in terms of architecture. In terms of learning, there are two very well-known algorithms that are used to train this. The first one is the greedy layer-wise, in which you train each of these RBMs independently. So that's what layer means. Take every layer, like train it independently and then connect them. So obviously you can imagine the complexity level, but that's like the first algorithm. And the second one is known as the wake sleep algorithm. What happens is in wake sleep is you train all the networks like in one pass and then like alternate networks in the other pass and so on. So it's more like a wake sleep type of a network. So you don't train every network in every pass. But like alternate networks in one pass and then the ones that were missed, you train them in the next part and so on. Again, there is this like link that I've provided that actually talks about deep belief networks. And Dr. Jeffrey Hinton, the person who actually came up with this idea of deep belief networks, there's a paper, I think, that you can read. So this will give you a detail of what deep belief networks are. And then there are these references if you're interested going into further details about this. But I would say these are really advanced topics, and most likely you don't need them now. But as far as understanding goes, if you understand the restricted Bozeman machines, I think this shouldn't be that hard to relate to. Okay, so that's that. And then there is another one, which is the deep Bozeman machine. Now, as you can see, from both of them, the fundamental difference between both of them is that deep belief networks in some sense have some layers that are directed, right? So they don't allow both sides of information sharing. But in this one, a deep Boltzmann machine is 100% Boltzmann machine in the sense that you can see these are not directed, right? So I've stacked multiple Bozeman machines one over the other, obviously making it more complex. But the overall architecture differs from deep belief networks because the last two layers of deep belief networks are usually directed. So that's the difference between deep Bozeman machine and deep belief networks. Again, there is a source here. You can go and check that paper. But yeah, that's all about Bozeman machines that I wanted to talk about today. Let me quickly go over this one, the link to the Colab notebook that I was talking about. Now, as I said, we don't have any homework on Bozeman machines. So this implementation is done on this movie lens data. I don't know if you're familiar with that or not. Oh, oops. Why wouldn't it? Anyways, you can always Google movie lens because that's the most basic, I would say, data set for recommender systems. So here I just try to take that data set and implement Bozeman machines. And obviously I didn't do any thing extra. There are packages available to do that. And because it's, as I said, it's not a homework, so you haven't obviously tried that yourself. If you're interested at all for your projects or otherwise for any other side project you're doing or any research you're doing, this could be a point to get started with, right? So I provided that and the link to that. And yeah, if you're interested more in Boltzmann machines, definitely read this paper because this actually summarizes everything right from the basics up to the more complex deep Boltzmann machines and deep belief networks. Okay. All right. So that's all actually I wanted to talk about. Are there any questions or anything that you wanted to discuss? People who are online? Okay, so that's all I have for today. There aren't any questions. Thank you so much for joining, and yeah.